Welcome to this video about the reverse engineering process using Solid Edge. The reverse engineering process allows us to obtain a parametric computer-aided design based on the references from scan data, most of the times this being a mesh file such as STL. In this video, we are going to carry out the reverse engineering process of a scanned object, in this case this grinder, which we have scanned with the InScanHX, and we will obtain a CAD file, something that we can export to step file format, for instance. The software used to do so will be Solid Edge Shining 3D Edition, which is a CAD package that integrates certain reverse engineering tools that allows us to design using a scan as reference. This will not only boost the efficiency of the process, but also it will improve the accuracy of the results. It doesn't matter if you are an absolute beginner or if you are an advanced user. I hope you find this video useful and interesting. Let's get started. First step we are going to take is opening the mesh in the InScanHX software. Let's move to the post-processing tab and let's locate the mesh file. This part was scanned with the InScanHX using the laser scan mode at a resolution of 0.1 mm point distance. This is a very high resolution and therefore the results consist of, as you can see, over 6 million triangles. This is a heavy mesh file and it would be hard to work with in Solid Edge. For this reason, the first step will be making this mesh lighter so we can work in an efficient and effective way in the CAD package. The actions we are going to take are the following. First of all, we will run the mesh optimization and we will apply a 100% value. What this tool does is optimizing the mesh to its shape. The size of the triangles decreases and therefore the amount of triangle increases in the regions of high curvature. The optimization combined with the simplification will output a mesh optimized to its shape and lighter. Regarding the simplification, to work with Solid Edge, we would need a mesh in the order of 10 megabytes. In other words, this means a mesh of around 200,000 triangles. As a rule of the thumb, I would suggest to not exceed 500,000 triangles. For this reason, I will simplify it to 97%. The software estimates that the resulting mesh will consist of around 200,000 triangles, which is fine. Now click on Confirm to complete the action. And as you can see, now we have a mesh consisting of 197,000 triangles, which is way lighter than the original. That means that it is optimized. With less triangles, we keep the same information and amount of details. Now we are ready to export the mesh. and I recommend to always write in the name the post-processing actions you have taken. In this case, I will add 100 optim and 97% simplification. Now we are ready to move to Solid Edge. After opening the Solid Edge software, we go to Open, and we browse in our PC to locate the mesh that we have edited. If it doesn't appear, please ensure that either all documents or STL is selected. Before opening the mesh, let's go to Options and make sure that the millimeters is selected for the file units. Solid Edge has different work environments. Among them, only the part or the sheet metal environments have reverse engineering tools. Due to the nature of this part, we will be using the part environment. At first glance, it might look like the part is not being displayed, but this is because the part is outside the view area. To fix it, select Fit in the View tab. Or alternatively, you can double-click the scroll wheel of the mouse. Well, let's tackle the first problem, which is aligning the part to the coordinate system. To do this, we will go to the Reverse Engineering tab, and we will create regions to fit features. Firstly, let's select some triangles corresponding to the cylindrical shape of the part. To unselect triangles, simply hold the Control key. Okay, right-click to confirm, and then use the Fill tool to complete the selection. Let's do the same on the other side. We will need to create more features for the alignment. We will use this plane here. To select it, we choose a different color and continue with the manual region identification. Finally, let's identify a new region corresponding with the plane on the base. That should be enough data. And once we have defined the regions, we are good to start fitting features to them. I will fit a plane to these three regions. To select multiple regions at the same time, simply hold the Control key pressed while you select them with the mouse. Right-click to confirm, and we will also fit a plane there. And finally, we select Cylinder, select the two corresponding regions, and right-click to fit a cylinder. Let's hide the mesh for now and observe the result. We are going to use these features to create a coordinate system that we will use to align the mesh. Let's move now to the 3D sketching tab, and let's start with the align. By snapping to the center of the top and bottom circumferences of the cylinder, the drawn line corresponds to the axis of the cylinder. Now let's add a 3D point on the cylinder axis and connect this point to this plane. This point here will be the origin of the coordinate system. Now we need one line for the x-axis and one line for the y-axis. We draw two connected lines in the 3D space and we make them perpendicular. Afterwards, we connect them to the origin. And we force one of these lines to be parallel to this plane. To complete the operation, let's make this line be on this plane. And the same for this one. We have now all the features to create a new alignment. Let's show the mesh. Let's move back to the Reverse Engineering tab and click on Align. We select the mesh and we right-click to confirm. There are 4 different ways to align a mesh in Solid Edge. The one that we are using now is the Use Geometry References. To avoid snapping on the mesh, I will hide it. It's still displayed, but the mouse doesn't snap there anymore. And I will follow the instructions given in the prompt bar. Select the point on the mesh body to place the origin of the coordinate system. I know now what I need to do. Simply select the point corresponding to the origin. Now select another point to define the x-axis. We select the point and finally select another point to define the y-axis, which is this one here. You can already see that the coordinate system has been located to the desired place. Right-click to confirm, and finally the mesh moved to the coordinate system. Let's display it. Unfortunately, the features we created, the cylinder and the two planes as well as the 3D sketch, do not move along with the mesh. Let's simply delete them. The mesh is now aligned to the coordinate system and we are good to start with the reverse engineering process. Before that, let's take this moment to save the data. Now that we are ready to start with the reverse engineering process, let's decide how to approach it. My recommendation is to start always with the basic feature. In this case, we will start with the cone, the cylinder, and the smaller cylinder on the bottom. To do this, we will create a section sketch. Select the mesh and the plane used to dissect it. In this case, the front plane. If I hide now the mesh, we can see the section at the intersection between the mesh and the front plane. We will use this section as reference to start defining the sketch. Let's start by locking the sketch to this plane. And let's draw something that resembles the body of the object. Be careful not to create undesired relationships in the sketch. Once we have completed the basic sketch, it is time to guess and to find out the dimensions of the object. We will give a design intent to this reverse engineering. That means that we are going to use the measurements and dimensions that an engineer could have used to design this part. Let's try to find out what is the height of the part. This process is about trial and error. 99 millimeters for the height looks good. Let's now tackle the radius of the cylinder, which should be something about 19 millimeters. And also, let's define its height. Say 25 millimeters might be too much. We can leave it at 23 millimeters so far. Let's focus on the small cylinder on the basis. Its radius should be around 9.5 millimeters. Its height looks well at 9 millimeters, and we will also need the radius on the top. Probably something in between, or even a slightly smaller value. Okay, then 10.4 looks like a good match, and it seems to be fitting very well. I think we are good to revolve the face to create our base body. And there we go. We obtained this way the base feature. Let's hide the section sketch and the reference plane. And anytime in Solid Edge, we can go to the Reverse Engineering tab and check how good is our reverse process going. We select the deviation analysis and select the mesh as the reference object and select the design body as the test body. It is possible to define which distance to check and the tolerances. This way we can check how good it is going. It looks good so far, so let's save the progress. Let's continue now with the next step of this task, which is going to be the most challenging. We are talking about the helix. To face it, we will use the same section sketch that we have created before. Let's show only the section sketch. The way to approach it will be the following. We will first of all extract the cross-section of the helix. Afterwards, we will design the helix that defines the path that the cross-section needs to follow along. That way, we will be able to sweep this cross-section and obtain the desired shape. Let's get started. First of all, let's log to the front view plane, and first step I will take is trying to figure out if this helix has a constant diameter. To do this, I simply draw a rectangle that encloses all the cross sections. At first glance, it seems that the diameter is constant. Let's then figure out the radius of the helix, which seems to be 33 millimeters. Next step would be designing the cross section at the beginning of the curve, which is this point here, right? However, due to the poor integrity of the mesh at the intersection with the front plane, I will use any of these three other for references. Well, you already know the drill. What we need to do is, first of all, drawing a sketch that approximates to the shape. And now it is a matter of adding restrictions and dimensions to the sketch. Let's give it some more thickness. Let's try with an in-between value, say 125 millimeters, which seems to be a good match. Now we can focus on the angles of this cross section. Let's give it some more angle. 96 degrees looks good. And let's go with the next one. That's definitely too much, too less. So something in between. This angle looks good now. And finally, let's give another restriction to complete the operation and give a gap of 1 mm with the revolve axis. This way we will make sure that our helix is always inside the cone along its length. That guarantees the successful Boolean union operation that will come afterwards. Now that we have the cross-section designed, let's move it to the initial points. To do it, we use the Move tool and we make sure that the option Copy is enabled. We enclose the sketch and all the dimensions and we select a point to move from. We place the sketch on the desired location by trying to eyeball it in an accurate way. We are done with the cross-section. Before closing the sketch, let's also take the opportunity to copy the sketch again and paste it to the position corresponding to the end of the helix. This way we can approximately extract the pitch of the helix. By measuring the distance between points, we get a value of 60.66 millimeters that we are going to use now to draw the helix. Let's show the mesh and exit the sketch. Let's move now to the Surfacing tab and select the helical curve. With this tool, it is possible to easily define a helix by selecting an axis, and a starting point. Okay, let's flip it and let's give it the value we found for the pitch, which is 60.66 millimeters. You can observe that, as expected, the start and end point match. However, along the path of the helix, it doesn't match. Well, that's because it is a variable pitch helix. Let's give it a try to variable pitch. We need to enter a value for the start and end pitch. Let's try with 70 and 20 millimeters respectively. With the current data, it is not easy to guess these values. So we are not going to use this operation. Another option available is using an equation-driven curve. By using the equations of the helix, we can play with their coefficients to try to figure out a parametric curve that approximates to the geometry of the shape. This way to design curves is especially useful if you know the equation that defines the curve. In this example, we can play with the coefficients to try to adjust to the scan. However, this would result in an excessive amount of work. So we are not going to use this tool, but I found it interesting to introduce it here. We will try a simpler approach that will give us accurate results. It can be observed that the helix is enclosed inside a 33 mm radius cylinder. So let's draw this cylinder. We create a sketch on the bottom plane and draw the 66 mm diameter circle. Let's close the sketch and let's move to the surfacing tab to extrude the cylindrical surface. Now we can observe the intersection between the cylinder and the mesh. We will use it as reference to draw the helix. The tool used is the contour tool, which draws a curve directly on the selected surface. Let's give it a try. The selected surface is the cylinder. The initial point is the corner of the cross section. We switch now to face. And we start to eyeball and mark points at the intersection between the helix and the cylinder. The less points I select, the smoother the resulting helix will be. For the last point, we select a point beyond the end of the helix, approximately there, and we can modify its location until we are satisfied with the result. Okay, right-click to complete the operation. Let's now hide the cylinder and observe the curve we just designed. It can be observed how well it matches the helix, which was so hard to design with the previous tools we have seen. Let's hide now the mesh and display the design body. Before doing the sweep operation, I will add a new body. This way, the result becomes an independent body and it is not automatically merged to the main body. This Boolean operation can be done afterwards. Let's select sweep and let's make sure that single path and single cross section is selected. We select the path and then the cross section. Make sure that the orange dot is at the intersection with the curve. The result might not be the expected one, but that's because an extra step is missing. We need to select the axis of rotation. However, in this case, the software warns us that the feature contains faces that are self-intersecting, and it can therefore not be created. The reason why this is happening is because of the distance being too short, this gap here. Let's simply delete this dimension and let's increase its value to give it more room to the cross section to rotate. Before doing the sweep, remember to add a new body again. Let's do now the sweep operation again. Select the path, the cross section, and then the axis. Now we obtain a solid that approximates accurately to the shape. Let's take a moment to save the progress. Let's continue the process by copying 2 more times the helix. Let's hide everything but the helix we have just created. And thanks to the synchronous mode, we can make use of the solid edge gumball. Place the gumball onto the origin. Make sure that the snap to endpoint option is enabled. To rotate the gumball, press and hold the Shift key while you click on the blue circumference. Now make sure that the copy option is enabled and turn the part around the Z-axis 120 degrees. Repeat the process with the newly generated body to obtain the third helix. When observing the mesh, it can be seen that they are cut with a conical shape. Let's try to reproduce this cone. To do it, we will make use of the reverse engineering tools. Use the manual tool to identify the regions corresponding to the cone. Okay. From the Fit Surfaces tool, choose the cone and select the three regions. The conical shape has been created. However, we have no warranty that the cone is coaxial with the Z-axis. Since this is a design intent reverse engineering, we will force it to be coaxial to it. We will use the cylinder we created as reference. In the Home tab menu, let's make use of the Face Relate tools. We make the cone concentric to the cylinder. In clear blue, you can see the newly positioned shape. Now the cone is coaxial to the cylinder and therefore to the Z-axis. Let's hide the cylinder and show the three helixes. The conical surface will be used to split these three bodies. However, the cone is not completely cutting the bodies, so we need to extend the surface. In the Surface tab, choose the tool Extend and select the inner edge to close the cone. Now we are good to split the bodies with the cone. In the Home tab, under Add Body, select the option Split. Select the body to split, right-click and select the cone. The body has been divided into two independent bodies. Repeat the process for the other two helixes. We can either hide or directly delete the remnant. At this point, our design consists of four independent bodies. So let's carry out a Boolean union to combine them into a single body. We have reproduced the largest features of the object. So let's now focus on the smaller details. If we show the mesh, we can observe certain rounding between the helix shape and the conical body. Let's try to reproduce it. Select the round tool and select the edges to create the round edge. If we show the mesh again, we can change the round radius until we are visibly closer to the round edge from the mesh. Two millimeters looks like a match, so let's keep this value. Let's take a look now at the base of the object. It has two cuts on both sides and two smaller cylinder-like shape. So let's focus on them. You already know how the process works, so you might be already familiar with the process that comes now. For these two cuts, we will create another section sketch. So go to the Reverse Engineering tab, select Section Sketch, select the mesh, and select the plane. Let's hide the mesh and use the section sketch as reference. In the Sketching tab, let's start with a line and lock to the right plane. To begin with, we draw the You might have noticed that sometimes the line that the sketch snaps to is not coincident with the geometry that we see. Well, let me show you why. In Options, go to View and see that the arc smoothness value is set to 3. Change this value to H. Now the circles are displayed with high resolution and therefore we can now see that the edge of the cylinder and the snapping point coincide. Let's add now some restrictions and dimensions to the drawing. This looks like a good result. To duplicate it to the other side, we will make use of the mirror tool. Again, make sure that the copy option is enabled. Select the drawing and select an axis for the mirroring. We are good now to extrude a cut with these two faces. With the Shift key, the symmetrical extrusion is activated. We have now our cuttings. And to do the cylindrical-like cuts, let's take first another look at the mesh. We are going to use again the section sketches. However, this time the feature is not intersecting with any of the main planes. Therefore, we need to create a plane. Using this plane as reference, we can create a new plane and place it wherever the region of interest is. Let's use it now to create a new section sketch. Now we have the references to start with the drawing of this shape. However, we don't know the depth of the cutting. So let's first tackle that. With the reverse engineering tools, create a new region to fit a plane at the end of the cutting. To keep the design intent, let's force the plane to be parallel to the right plane. Use the face relay tools to do so. Now we are good to start with the reverse of this feature. Create another plane a bit farther to start the sketch there. Now create an accurate sketch that reproduces this geometry. We can use a vertical construction line from the origin to force the sketch to be symmetrical. Once the sketch is complete, we can use it to extrude the cutting. To switch between add or cut extrusion, press the spacebar key. Select From To and select the plane we created to define the extent of the cut. Show only the design body. And now let's mirror this operation. Select the cutout and use the mirror tool to mirror it through the right plane. We are now almost done with the design. We will focus now on the last feature of the object, which is the base with the threaded hole. To reproduce the feature on the base, we will again make use of the section sketches we have created before. Let's show only the section sketches along with the design body. Create a new sketch, lock the plane, and start drawing the approximate shape of the cuts. Add restrictions and dimensions to the sketch. We will use the sketch to revolve a cut around the cylinder. We have another cut with a particular shape. Let's see how we can approach it. We draw a circle, give it certain diameter, and try to eyeball its location. When trying to place the circle, I realized that the center of the circle might be connected to the edge of the cylinder. So let's add this restriction. Now we draw two lines, connect both ends, and use the trim tool to create a closed sketch. Let's focus now on the aperture angle of this shape. 60 degrees seems a reasonable value. Let's complete the operation adding another angle. However, it looks like this shape might present a symmetry through the circle. So let's force this restriction. We draw the symmetry line and give it certain angle, say 45 degrees. With the symmetry restriction, we define the symmetric axis and the symmetrical elements. The sketch looks good, so let's do now the revolve cut. Observe the result. There is a chamfer at the base. It looks like it has unequal setbacks, so we select this tool. Select the plane and then the edge. The given values of 0.6 mm setback at 40 degrees seem to match the geometry, so we will accept the operation. Let's hide now the sketches and PMIs and observe the result so far. Let's save the progress. And the last feature that we are going to reproduce in this video is the threaded hole at the base of the object. Let's look at the mesh. There is a threaded hole. Let's see how the section sketches we created before can help us to reproduce this feature. The front view contains not much information about the thread. However, the right view contains more details, so let's use it as reference. We will create a new sketch to draw some reference lines. Let's draw a rectangle to figure out the diameter of the thread. First thing we observe is that this is a parallel thread. It is not conical. And that it must have a diameter of around 12.15 millimeters. The second thing we can observe is the pitch of the thread. Let's draw some reference lines to make measurements. We draw multiple lines to be able to compare the different measurements. When adding the dimensions, we observe that the pitch of this thread must be around 1.25 millimeters. Let's use these values to identify the size of the thread. We show the design body and we close the sketch. Under the Home tab, select the Hole tool. Let's take a look at its options. Select the threaded hole and click on this button to load the database. In this Excel file, we can find all the different threads from the Solid Edge database. Let's look for a thread which has the size of the hole. The hole we are looking for has an internal diameter of around 12.15 millimeters. It must therefore be a M14 thread. There are two different pitches for the M14 thread though. In our measurements, we found out that the pitch must be 125 millimeters. So the thread we have to draw is therefore the M14 1.25. Close the database and select this thread from the drop-down list. The hole we have is a through hole, so we select the through all option. The thread extension will be the entire hole, so we select to hole extend. Finally, we will add certain chamfer. We don't have its dimensions though, so let's take the time now to measure it. Likewise, draw reference lines to extract the dimensions. The chamfer seems to have a size of 1 millimeter and the angle seems to definitely be 45 degrees. So let's use these values. Select the hole tool again and set the same parameters. This time we can add 1 millimeter offset and 45 degrees for the angle. After clicking on OK, we will have to look at the plane where the hole starts and snap to the center of the base to place it. A cosmetic hole has been added to the model. Let's display only the design body. Let's display the mesh tool. And now we will run the deviation analysis to check the accuracy of the result. The reference body is the mesh, and the test body is the solid we designed. The analysis will require some time, so we will cut the video. With this tool, we can observe the quality of the result in terms of accuracy. In the statistics, we can observe how many samples are inside the outer tolerances, defined by the positive and negative outer, and the samples inside the inner tolerances. We can change the values to be more restrictive and check how accurate our reverse engineering is. 46% of the samples are within the range plus minus 0.05 millimeters. Overall, this seems to be an acceptable job. So, and we are not going to reverse the nut on the top of the object in this video as it is not of interest. Take a moment to observe the analysis. Once you are done, click on Close to exit the interface. Before ending this video, I wanted to show you how to obtain a physical thread out of the cosmetic thread in case you wish to 3D print this part. Under the 3D Print tab, select the Physical Thread tool. Simply select the cosmetic thread and accept. Solid Edge easily generates the thread. To finish the video, we enable the high quality view and give the part a chromed material. I hope you found this video informative, useful, and that it brings ideas to approach your reverse engineering projects.